Donc je voudrais remercier Jan Kunes d'avoir accepté de venir donner ce séminaire et rester quelques jours dans notre équipe. I'll switch to English to present him. We're very glad to have Jan visiting for a few days and accepting to give this talk here. Jan originally is a physicist who was more interested in materials and density functional theory and electronic structure for his PhD in Prague. But then he became very interested in electronic correlations, moved to Augsburg, where he did a Humboldt Fellowship and postdoc with Dieter Wohlhardt. I guess that's where he met the MFT. And he's had a very, very successful career and contribution to the field. It's a bit difficult to quote all the things he's been working on, but I've been particularly interested in sort of excitonic magnetism, for example, and low-spin, high-spin transition in many systems. One of his recent interests is actually more broadly defined the concept of excitonic condensation, and this is what he's going to tell us about. I already mentioned the review article that he's written on this recently. Jan is now based at the TU in Vienna. He still retains an affiliation to the Prague, to the Czech Academy of Science, and he was also the laureate of one of these prestigious ERC grants. And after this introduction, without further ado, the floor is yours.
So, bonjour, Madame et Monsieur. So that's about my French. Thank you to Antoine for inviting me. It's a pleasure to be here and also an honor. So I'm going to talk about excitonic condensation in strongly correlated electrons. A different title of this talk could be a magnetism of non-magnetic ions. So imagine that you have an atom where the ground state is a singlet state, and there are some higher excited magnetic multiplets. And we ask what happens when we build a lattice of such atoms. And of course, this sounds like a pretty stupid thing to do, something like combing a bald head, because we don't have any 3 degrees of freedom to order or to get something interesting out of it. Nevertheless, you still can make quite a lot of physics out of it and make life with this kind of topic. And the reason why you can do it, of course, is that if you build a lattice out of such atoms, the interactions between the atoms may bring these higher magnetic multiplets back into the game if they are not far away. Let me give you a few examples or motivations to look at such systems or such materials. So the first one is this praseodymium calcium cobaltate, which is a material from a broader group where the parent material is lantern cobaltate. And in this family, there is a collective transition or a phase transition, which one can see in magnetic susceptibility, transport, and so on. And it is the question in this material is what is the order parameter? Because there is no magnetic order detected so far, so one can call it a hidden order material, which would be a nice word to sell it. So I will talk about this material a little bit towards the end of my talk. The physical parameter which brings in this singlet, triplet, or singlet higher multiplet physics into play in this material is crystal field. So you can imagine that you have a D shell in crystal field which is split into an EG and T2G subshell. And with cobalt 3+, you have 6 electrons, so the low spin state would be a state where you put all 3 down here, and you have the singlet, and then you can build higher order or higher moment states, for example, this intermediate spin state, which would be the exciton, as I will show you. Another material that has been discussed and investigated in the context of this excitonic magnetism is calcium ruthenate. And here the physics of singlet triplet excitation is brought about by the spin-orbit coupling. If you put a D shell into crystal field and you have a strong spin-orbit coupling, you further split this T2G shell into a quadruplet and a doublet. So if you have 4 electrons, in this case, like in ruthenium and calcium ruthenate, you put 4 electrons in here, and you have a singlet ground state, and you can build then again excited states with some spin degree of freedom.
So excuse me, Jan.
Yes?
Or somebody else, can the lights on the front of the board be controlled? It's kind of hard to see what you're actually writing.
Oh.
If you want to write more on the board.
Yeah, so then we'll live with that. Is that better?
Yeah.
Okay, I'll switch it off in a moment. I'm not going to use the board much. So the next example to motivate is this thulium copper trichloride, which is a material where again we have the singlet triplet physics. Now this physics does not arise on a single atom, but on dimers, which are the structural building unit in this material. So you can imagine that you have a material where you have antiferromagnetically coupled dimers, which are coupled by some weaker coupling, and you have spin 1/2 on each side. Then in this dimer basis, you can have a total singlet or total triplet, and depending on whether the coupling between these dimers is strong or weak, you will have either a trivial or a singlet, global singlet ground state, or some non-trivial long-range order. And this can be tuned with rather small pressure in this material, and so these are experimental studies of the magnetic collective mode, which come from this work of Merchant and collaborators. Well, the physics that is related to this kind of magnetism is actually much older. It goes back to the concept of excitonic insulator and to the work of Neville Mott in the early 60s and others later on. And the idea of Mott was the following: if you have a band insulator with a small gap, if the attraction between electrons and holes is stronger than the gap, then you will form a new state of matter, which will be this excitonic insulator, which can be also viewed as Bose-Einstein condensate of these electron-hole pairs, so excitonic Bose-Einstein condensate. This idea was investigated a lot in the 60s in the context of weak coupling, BCS theory. It has been revived more recently by the work on that are shown here. There is another big field which so is there an experimental realization? Well, there are some experimental proposals in materials, but the experimental realization of this excitonic condensate so far was found in artificial heterostructures. So these are beautiful experiments by Eisenstein and McDonald from 2004, where they built a bilayer of quantum wells. So they had two-dimensional electron gases which were coupled to each other. And what they measured was hole conductivity. So they were changing the magnetic field. By changing the magnetic field, they were tuning the electron and hole concentration in these two layers. And so you observe that in one layer you have electron-like hole conductivity. In the other layer you have hole-like hole-like hole conductivity. And if they get to a rather narrow region where the concentration of hole and electrons were approximately equal, the signal went away, which was a signature of these electrons and holes forming a neutral bound pair. Of course, this is not a proof that we have a coherent condensate. To prove that they have a coherent condensate, they measured the tunneling rate between these layers. And this is a tunneling rate in the normal state when there is no condensate. And then when they get to this excitonic condensate regime, they saw a huge peak at the zero bias voltage, which was the proof that there is indeed a coherent condensate of excitons. There is yet another big field of this excitonic condensation, which our host has become recently also active in, which are exciton-polariton condensates. So these are mostly semiconducting materials where the electrons and holes are coupled to a cavity electromagnetic field, and this leads to also to possibly Bose-Einstein condensation of these objects. So this is the outline of my talk. So I'm going to start with the minimal model of this excitonic condensation, which is two-orbital Hubbard model. I will talk about the strong coupling limit, which I think is the most instructive to explain the physics. And then I will show you some results obtained with dynamical mean field theory. So in the context of the previous lecture, this should be viewed as an application of dynamical mean field theory to systems where a symmetry is spontaneously broken. And then in the last part of my talk, I will talk about real materials realization, so a little bit more details about these cobaltates, and I will touch the question of how we can actually detect this excitonic magnetism or excitonic condensation experimentally. So let me start with the model setup. So to get several different multiplets, we need at least two orbital atoms. So we start with two orbital atoms where we have some crystal field splitting between the two orbitals. You can think about geometrically about these x squared minus y squared and xy orbitals. And we'll consider the local electron-electron interaction, including the Hund's ferromagnetic coupling. So if we look at the two electron configurations, we can sort out these 6 different states. So a singlet where we have 2 electrons in the lower band. Then we can have a triplet where this is what I will call high spin. Then we have another singlet and another singlet where we have 2 electrons in the upper band. And these are the corresponding total energies, atomic energies. And for the purpose of our further developments, I will forget about these excited states, and I will focus on the situation where the energies of these two states, so the low spin state and the high spin state, are not very different from each other. So which means that the crystal field should be approximately equal to 3 times the Hund's coupling. So now I guess I can switch off the light again. Oops. Okay, so now let us put these atoms on a lattice. So I will show you specifically results for a square lattice, but for dynamical mean field theory or for this strong coupling theory that I'm going to show you, the lattice geometry is not really important. And we will consider no interaction between the nearest neighbors, so that will be Hubbard model with purely local interaction. And we will consider hopping that is dominantly between the same orbitals. So this would be typically a perovskite structure where you have hopping only between the T2G and T2G and EG to EG. And we will consider some small hopping between different orbitals. So in a real material with perovskite structure, you can imagine that you have some tilting of the octahedra, which would give rise to this kind of hopping. So now let us go to the strong coupling theory where U is or the interaction energy scale is much larger than the hopping. And so what we do in that case, we will develop a perturbation theory in the hopping. So let me show you a few possible processes. So we can start with the 1 atom in the low spin and 1 atom in the high spin state, and we can have such an excursion back and forth, or an excursion in the lower band, which would of course reduce the energy of high spin low spin dimer with respect to 2 isolated atoms. But we can have also an excursion where the upper electron or where the lower electron hops to the right and the upper electron hops to the left, and then we will have exchange of high spin and low spin in the same order of perturbation theory. And of course, now you can kind of write the whole list of these of all these second order processes. So you can have this high spin, low spin attraction, which can be viewed as a repulsion of two high spins that are sitting on the neighboring sides. You can have this process which can be viewed as a hopping of the high spin excitation. If you include these cross hoppings, you can also have terms that look like a pair creation of two high spins. Now the natural language to describe this strong coupling Hamiltonian with is the language of spin 1 bosons. So in this language, the lattice filled with low spins everywhere is the bosonic vacuum, and now a high spin on one atom on the lattice is a bosonic excitation of this vacuum. And the reason to introduce this language is that these bosons or these excitons are actually mobile. That's the important observation, and this is the process how they can propagate on the lattice. So this excitation is not an atomic-like excitation, but it is rather an exciton that can hop from side to side. So let us now look at the at the strong coupling Hamiltonian in where we have all the terms. So we have the first term is just the chemical potential of the bosons, which depends on the difference of low spin and a high spin plus some renormalization. Then we have a term which describes the hopping of the bosons on the lattice. Then we have a term where we have the nearest neighbor repulsion between the bosons, which does not depend on their spin. And then we have a term which is spin exchange between these bosons, so kind of the standard super exchange term. Such a model can be rather accurately described by a simple mean field theory. So this is the mean field phase diagram of such a model. Let me start on this side. So this would be a side where this epsilon is negative. So the low spin is basically irrelevant. In this case, all these terms reduce to just constant, and we are left with the Heisenberg model describing the interaction of the high spin spins. Then if we are in the region where the epsilon is small, so meaning close to zero, and this nearest neighbor repulsion term is dominant, we will get a crystallization. So we will get a high spin, low spin, high spin, low spin order, which is essentially a crystal of the high spins built on this low spin vacuum. And then when we go to the very right end, where the epsilon is large, meaning that the energy of the high spin is much larger than the energy of the low spin, we will get a trivial state, essentially the low spin vacuum. Now, if you look at the elementary excitations of this low spin vacuum, it will be this high spin boson. As I explained, this boson will not stay stationary, it will propagate, and that's why it will acquire some bandwidth, some dispersion. And now we can ask what will happen if we start from this right side and reduce this energy of the high spin. So we will essentially be closing this bosonic this excitation. Oops. Okay, so this is an actual calculation. This is actually spin wave, linear spin wave theory for this kind of model. And you see that as we first reduce the gap, basically rigidly shifting the dispersion, but when the gap is zero, because we have bosonic excitation, their energy cannot go negative. They will condense, they will form a Bose-Einstein condensate, which is this excitonic condensate phase, and we will get correspondingly some Goldstone modes and other collective modes that I'm going to talk about a little bit later. Now, let us talk about the nature. What is how shall we understand this excitonic condensate phase. So it is a state where both low spins and high spins are partially occupied, but it's important to distinguish this state from a normal state at a finite temperature, because we can also have, if we are somewhere here, the low spin and a high spin will have some fractional occupation because of thermal excitation. So in that case, on every side we will have a statistical mixture of a vacuum state and a bosonic state. So this occupation of bosons will be larger than 0, it will be finite, but the bosonic field will have a zero expectation value. In the language of fermions, we will have some thermal population of the high spin states, which will respond as a free moment. So experimentally we will see something like 1/T Curie-Weiss susceptibility, but there will be no anomalous terms in the occupation matrix. Now the excitonic condensate is a different type of state. This state you can rather accurately model as a product of superpositions of the vacuum and the bosonic state on every side. So in this case, again, you have a finite occupation of the bosons, but the expectation value of the bosonic field is now non-zero. It will be proportional to the product of this A times B. In the language of fermions, we will have some coherent superposition of a low spin state and a high spin state on every side. And so if you calculate an occupation, if you calculate an expectation value of this orbital off-diagonal and spin triplet operator, you will get a non-zero value. Now, there is one thing that makes this condensation rather interesting, namely that we have several flavors of the bosons, that there is the spin, there is a degree of freedom, and that's why we can build different types of condensates. For example, if you build a condensate where only one of these bosons, so let's say with SZ equal to -1 condenses, the condensate will be obviously ferromagnetic. There would be a net magnetization, but you can also build a condensate where the -1 and +1 components enter with the same weight. And in this case, you will get a condensate which doesn't have any moment pointing in any direction. This condensate in the bosonic language, as I learned, is called polar condensate. And so I will use this name polar condensate from now on. So you cannot. So these are really different states, and you cannot by symmetries of the Hamiltonian, which in this case would be a spin rotational symmetry, you cannot rotate a ferromagnetic condensate to this polar condensate. They have different residual symmetries and are really different phases. Okay, so let me now go to fermionic theory. So we are done with bosons. Now let us look what happens when we go back to our Hubbard model and work with the language, with the fermions explicitly. To do this, we have to use computers and use some approximations. So we will use dynamical mean field theory. And the key quantity we are going to talk about is this expectation parameter, which is, or this order parameter, which has the form of this orbital off-diagonal and spin triplet expectation value. And later I'm going to tell a little bit more about how to visualize this order parameter geometrically. So on our phase diagram, we will focus on this region where we have only normal state and the excitonic condensate. We will go into a parameter range where there are no other competing phases. So we will be looking at phase diagrams of this type, using mostly the crystal field splitting as one parameter and temperature as the other parameter. The tools we are going to use is the dynamical mean field theory, which we've heard about today. The theory in a standard framework works on the one particle level with hybridization functions and Green's functions. Well, I will show you also some results on two particle levels, so basically susceptibilities and dynamical susceptibilities. And to calculate these, we have to go to a Beer-Salpeter formalism. Essentially what you're doing is kind of a post-processing of the DMFT results. You use the converged Weiss field, and with this Weiss field you calculate more complicated correlation functions. So let me start with some results. So what I'm going to show you are results for these model parameters on a square lattice. Important is the filling. We are working with the half filling, so we have 2 electrons on site on average, and we are looking at what happens when we cool down from normal phase to a region where we expect this excitonic condensation. And the questions we may want to ask is, are we going to see this condensation to happen? And what kind of condensate are we going to get? Are we going to get this polar condensate, or are we going to get ferromagnetic condensate? In the bosonic language, what decides which of the condensates we are going to get are the other terms in our Hamiltonian. So the condensation is driven by this hopping of fermions, but the type of the condensate depends on terms like the spin-spin exchange, for example. And I'm going to talk about this a bit more later. So this is the first numerical result. So this is temperature, and here we measure the autoparameter, and you see a typical mean field lag dependence of the autoparameter. So indeed, we get a finite expectation value of this orbital off diagonal spin triplet autoparameter, and we find that the condensate is actually of the polar type. In a moment, I'm going to explain how we can see it. We can look at several quantities which characterize, which have, let's say, interesting behavior due to this condensation. So the first one is a uniform susceptibility. So this is again temperature, uniform susceptibility. Here the shaded area is the condensate phase. So if you force the system to stay in the normal state, you see this Curie-Weiss-like behavior. As I explained before, this comes from the thermally excited high spin state. Well, at the condensation, the high spin still remains in the system, so the susceptibility does not go to 0, but it remains temperature independent. So the high spins cannot now respond as free local moments to give you this 1 over T behavior. This is actually a quite simple explanation. If you're interested, you can ask at the end, but I'm not going to go into that now. The other thing we can look at is the spectral density. So this is fermionic spectral density, something that does not exist on the level of the bosonic model, of course. And what you show here, what you see here, is the spectral density of the A and B electrons in the normal state. So these different curves correspond to different temperatures. Here's the high temperature region, and this is decreasing temperature. And you can see in the normal phase we have essentially 2 touching bands, so A-like band and B-like band. And as we go into the condensed phase, a gap opens. And if you're familiar with just S-wave BCS superconductivity, this should look quite familiar. You have a 1 particle gap with these peaks, which in superconductivity are called Hebel-Schlichter peaks. And this is indeed no coincidence. There is essentially exact mapping between this excitonic condensation and superconducting transition. So on 1 particle level, they can be mapped on each other. If you look at the response to the electromagnetic field, there is of course a huge difference, because here we have excitons which are neutral, while in superconductor we have Cooper pairs which are charged. So this is the same picture in K-resolved fashion. So here you see the 2 almost touching, or 2 touching bands, and if we go to the ordered phase, we see this excitonic gap opening here. So indeed we get what Mott called an excitonic insulator. Now you can ask, where are the excitons in this picture? Well, the excitons are obviously not in this picture. The excitons in the language of fermions are two-particle objects, so we have to look at dynamical susceptibilities to see the excitons. And this is doesn't look so nice as on the screen of the computer, but these are various dynamical susceptibilities calculated for the model. So in this, so these different rows correspond to different temperatures. This right column corresponds to spin-spin correlation function, so this would be the spin dynamical structure factor, and these different columns correspond to a different excitonic susceptibilities. So if you're interested in the exact form, these are the corresponding operators. But so these essentially describe a dispersion of an exciton in the normal phase. And when we cool down to the ordered phase, you can see that we have this development of some linear modes, and that the symmetry of these susceptibilities is broken. Perhaps the more instructive way or intuitive way to look at this is not to look at the temperature-driven phase transition, but to look at the transition driven by changing the crystal field. This would be essentially the picture I showed you on that simulation in the bosonic picture. So this is these upper two rows correspond to the normal phase. So you can see a dispersion of an exciton with some finite gap. Then we reduce the crystal field, the excitonic gap closes, and when we get to the ordered phase, we get first of all the dispersion of these different type of susceptibilities is now clearly different, and we get two Goldstone modes. I'm going to say a little bit more about it later, but this one Goldstone mode corresponds to the breaking of the spin rotational symmetry, and the other Goldstone mode corresponds to breaking of a gauge symmetry, which is related with the conservation of the A electrons and B electrons separately, or in the bosonic language, it breaks the conservation of the bosons, which were encoded in our original model. One interesting observation, which I'm also going to comment a little bit more on later, is the evolution of this dynamical spin structure factor. In the normal phase, you can see there is absolutely no response. This is no surprise, because essentially we have a bent insulator which has no moments to flip. But when we go to the ordered phase, there is clearly a rather well-defined dispersive feature which look like a spin wave, but there are no ordered moments in this system. So this is an interesting point which can be. Is there a question?
Yeah, I just wanted to ask. So in the different phases that you investigate, are you actually breaking the continuous symmetry?
That's right. So what we are looking at is in these calculations is a Hubbard model with a density-density interaction. So the continuous symmetry is we don't have SU2 spin symmetry, we have only U1, but this U1 is broken because we have order parameter which lies in plane. So this is the continuous symmetry that is broken.
And this is the Goldstone mode.
This is the corresponding Goldstone mode. And then we have the gauge symmetry, which is the conservation of this A and B chart separately, and this is the other Goldstone mode. And this was, of course, from the motivation for us to look at this was that we were interested in how DMFT performs. We did not know whether DMFT is going to reproduce these Goldstone modes, which are, of course, expected based on the general symmetry considerations. And we also did not know how our numerical implementation is going, how well it is going to describe it or not. And I'm actually going to show you later that when we break this symmetry weakly, we are indeed going to see opening of a gap here, which is so rather small perturbation of the symmetry is reflected in this two particle susceptibility. So now let me take you to a zoo of other phases. So this is what happens when we start playing with this model and when we add doping and we add finite cross-hopping, so a hopping between orbitals of different type. And I'm going to break this up for you. So first, let us look at the excitonic order parameter and make some geometrical representation of it. So obviously, it is a vector that has some direction in the spin space, but because it is an orbital off-diagonal quantity, it is a complex number. So you can define its real part or imaginary part. You can also call it a density-like part, which would be AB plus BA, and a current-like part, which would be AB minus BA times I, if you want to have a Hermitian operator. And now, depending on the relative size of this real and imaginary part, and on the angle between them, we can define a different phases of our model. So let us first look at the effect of doping. So in this phase diagram, we have a temperature on the vertical axis and the doping on the horizontal axis. So far, we've been moving along this line. So we at half filling, we were changing the temperature. Now, if we introduce some doping, we can see the same effect that Eisenstein and McDonald saw experimentally. If you detune the population of electrons and holes, you quickly destroy the excitonic condensation. Nevertheless, there is a finite interval of dopings where the condensation still persists. And interestingly, before we can kill the condensate completely, we actually, by doping, induce the transition from polar condensate to the ferromagnetic condensate. Now, how can we understand it? Well, again, the strong coupling picture is a rather useful one. Of course, if you want to describe this system, this model is not enough. You should introduce also some free fermions. So you should have something like an analogy of TJ model. But to understand the phase diagram, it's actually enough to realize that what the doping does is it changes the sign of this spin-spin coupling. So in the normal phase, or in the undoped phase, we have an insulator where the super exchange, antiferromagnetic super exchange dominates, and if this K0 is positive, the order parameter, we get this polar condensate where the boson that condenses has this kind of form that it has some direction in the Cartesian representation. Let me put it this way: simply, it does not carry any magnetic moment. While if we dope, we induce through essentially a Zener double exchange mechanism, we induce a ferromagnetic exchange, and in that case, the polar condensate is favored, in which a boson which carries a large spin projection in some direction condenses. So if we look at this PEC phase in our geometrical representation, we get a real and an imaginary order parameter which are parallel to each other. Their amplitude, or in other words, the phase of this order parameter is arbitrary. So this is something which is the spontaneous broken of this gauge symmetry. Now, if we go to the ferromagnetic phase, the real and imaginary part are perpendicular to each other, and one can show that this implies that there is a magnetic moment pointing perpendicular to these two. It's actually rather simple to see why the angle between these two plays a role, because in the strong coupling picture, the local moment can be written in this form as a cross product of these two vectors. This is perhaps a rather not very intuitive way to write it, but if you decipher it, so if you write as, for example, if you look at SZ, it's dx times dy minus dy dx. If you go to the more familiar representation where SZ is the is the index. This is just equal to the number of bosons with Sz equal to 1 minus the number of bosons equal Sz minus to 1. So this is a rather simple relationship. Now there is also this intermediate phase where the imaginary and real part are still perpendicular but are not equal to each other. Okay, now let us look at the effect of cross-hopping. So the cross-hopping has a different effect. It adds another term into our bosonic Hamiltonian. It is this pair creation, pair annihilation term. So you can imagine that you start with 2 low spin atoms, and by this cross-hopping event, second order and fermionic hopping, you can create 2 high spins on the neighboring sides. And now, depending on the relative sign of this term and this term, you either form an order which is purely real, or you form an order which is purely imaginary. And this is again rather easy to see if you replace these operators with numbers. So, for example, imagine that we have a negative parameter here. So then you want to have an opposite sign, or then you want to have a staggered order to get an overall negative contribution to the energy. And now, if this term is positive, so we are in this region, then you want to have a purely imaginary number here to get again overall negative contribution. And so you can use similar reasoning for the other case. So now what is the physical significance of this? So if you have a real order parameter, you can show that your ordered state breaks time reversal symmetry, and it corresponds in the real space to some multiple ordering of magnetic multiple spin order. So exact shape of your spin polarization in real space, of course, depends on your orbitals. But for example, if you use this x squared minus y squared and xy orbitals, this kind of order parameter would give rise to this spin distribution around each side. If you're in this phase where the order parameter is purely imaginary, you can show that the ordered state does not break time reversal symmetry, and it can be described as a pattern of spin currents that are flowing within the atoms or also on the lattice. So this is let me now show you the computational results. So let's assume we take an even cross-hopping. Even cross-hopping means that the hopping to the left and hopping to the right have the same sign. We are going to get this the current-like spin current-like order parameter at 0 doping, and then we dope. When we dope, we are going to go to the ferromagnetic phase and eventually to the spin density wave-like order parameter. So we will go from purely imaginary order parameter to purely real order parameter here. If we start with odd cross-hopping, so if hopping to the left and hopping to the right has opposite sign, so this is easy to realize geometrically. For example, if the A and B orbitals have an S-wave, S-like and P-like character, then the hopping between them would have different signs when you go to the left and when you go to the right. We will have this sequence reversed. So we will go to spin density wave-like through the ferromagnetic EC phase to the spin current density wave-like phase. And so we can characterize the whole zoo of phases. We can look at whether they have some spin magnetization in real space. We can look if there is some local magnetic moment on the atoms. We can look at whether there is some magnetization in K-space. I don't want to go through all this because it's the main message is basically that there is a whole zoo of different phases. But let me point, okay, let me discuss two things. Yes?
So when you put this cross-hopping in, then you break this U1 symmetry, right?
That's right.
So now you break a discrete symmetry.
Now you break a discrete symmetry.
So you gap the Goldstone mode.
This is the answer to your question. Okay. So it's exactly what I'm going to show now. So now let's say we are at this point. So we have, if we have this gauge symmetry, so if the cross-hopping is 0, we have two Goldstone modes. We have this one, which corresponds to the breaking of the spin rotational symmetry, and we have the phase Goldstone mode, which corresponds to the breaking of this gauge symmetry. When we go to the case where we have this cross-hopping, this is what happens. So you see the spin Goldstone mode is still there because we still have a continuous symmetry to break, but the phase Goldstone mode now is not actually a Goldstone mode. It becomes, well, actually you can call it either a Higgs mode or you can call it a gapped Goldstone mode depending on its character. So depending on whether its spectral weight remains in the same sector, it still corresponds to rotation of a phase, but it's now gapped. So this is a very common situation in magnetic materials, right? You have a spin wave, but because of some magnetocrystalline anisotropy, you open a small spin gap. So this would be an analogical situation. But if this symmetry breaking is very strong, you would actually move the spectral weight from this phase rotation factor to an amplitude fluctuation factor. And if you are interested, I have one slide to show you that. Okay, so now let me go back to these phase diagrams and to point to the phases which are, I find, particularly interesting. And these are the two phases which do not break the time reverse symmetry. So this is something that, well, in some community would be called a spin nematic phase, a phase that breaks rotation symmetry in spin space but doesn't break time reverse symmetry. And we still have two different types of these phases. You see, there is no magnetization in real space, then of course no ordered moment, but we can still distinguish these two by asking question, can we see something if we look in the K-space? In this SCDW phase, there is nothing in the K-space. It means that these spin currents that are now flowing in our systems are purely local. They flow on the same atom between atom A and between orbital A and orbital B, while in this SCDW phase, we actually get a spin polarization that we can see in the K-space, and this is actual calculation of this quantity. Now, what does this mean? Does it mean that we have a uniform spin current flowing through our system, as this may naively appear? One would say, okay, we have electrons that are here are running in one direction and carry one spin polarization. Electrons that are here are running in the opposite direction, carry opposite spin polarization. Well, it is not so simple. Well, first of all, if it was the case, then we would violate one exact theorem that is known under the name Bloch theorem, which says that there cannot be a spontaneous charge of locally conserved quantity. And this is also not correct way to think about it, because the contribution to the current depends on the group velocity. And we have here two bands. The two bands may have, and in our case, they have opposite group velocities. So you cannot really read off spin current simply from the fact that you have some spin texture in your system. Nevertheless, it is interesting to look at other materials, or what can one do with such spin textures. And there are examples. For example, spin textures generated by spin orbit coupling has been recently used to manipulate antiferromagnets and switch magnetic orientation of switch the null vector of an antiferromagnet by applying a spin current. This is, however, in the realm of non-equilibrium physics, and of course, this is in general a very, let's say, hot topic in the field of these Rashba semiconductors with strong Rashba spin orbit coupling. Okay, so let me finish with the models here, and let me go to something down to the ground to look at the real materials. There are several examples, as I mentioned, that may be promising. This praseodymium calcium cobaltate, perhaps lanthanum cobaltate in external field, calcium ruthenate, and there are also materials which are considered. Now it's almost proven that these are excitonic condensates, which are not magnetic, where the excitonic condensation actually takes place in the spin singlet channel. Just to go quickly through this, if we go to real materials, the physics gets much richer, because we have not only a spin degree of freedom, so our excitons have not only spin, but they also can have some orbital degrees of freedom. So in D6 perovskites, we would have 3 orbital degrees of freedom and 3 spin degrees of freedom. So in total, we would have 9 excitons, and this would allow us to build many different phases, different excitonic phases described now by order parameter, which is actually a second rank tensor. And this one can indeed do. Perhaps not in the real materials, perhaps not for the realistic materials parameters, but we have obtained these solutions of the static mean field calculations, which generated all these different order parameters. Now, what about the real lanthanum cobaltate? So, is there an excitonic condensation? The answer is known for a long time. No one observed it. But the other question is, are there mobile excitons? And this is a very new result, where using the Riggs technique, our experimental colleagues were able to indeed map out this rather steep dispersion in this part of the Brillouin zone. Unfortunately, we cannot really probe this most interesting part, where is the bottom of the band. This is simply a restriction due to the photon energy. So this is a measurement at L edge of cobalt at photon energy of about 700 electron volts, and you simply don't have enough momentum to probe this part of the Brillouin zone. So this is still an open question. Now, what is the problem for excitonic condensation in lanthanum cobaltate? Why is it probably hard to achieve it in this material? The problem is that our excitons, which are the intermediate spin excitations, are actually strongly interacting with each other. So they tend to form high spin states, which are, in our language, B excitons. So this is like a situation where we have a strong intermediate, strong exciton attractive interaction. So this kind of reaction would probably hinder the excitonic condensation. On the other hand, if the intermediate spin states were not present, then the obvious question would be, why don't we observe high spin, low spin, high spin, low spin order, which is something that is expected theoretically to be observed. So this is an important question, and my personal suggestion is that it is the presence of these fluctuations. So the fact that the high spin is not really an atomic-like excitation, but is kind of a high spin dressed with these fluctuations of intermediate spins, that is the answer to the question. So one possible route to achieving excitonic magnet in cobaltates would be to somehow get rid of the high spins, and this can be possibly done by going to two-dimensional structures. Now, this calcium praseodymium cobaltate. What is this is a material where there is a real phase transition observed, and I told you a little bit about it at the beginning, but I didn't tell you from my point of view, the most interesting fact. The most interesting fact is that the ordered phase breaks the time reversal symmetry. How do we know? The praseodymium is in a doublet state. So we have a Kramers doublet, which is the ground state of this praseodymium. And if you look at the specific heat, one can see that this doublet is split. One sees a Schottky peak associated with this splitting. So it means this Kramers doublet is split, time reversal symmetry must be broken. How is it possible? The natural explanation would be some kind of magnetic order. So this was, of course, what a lot of people thought or realized. So they looked for this order, but it was never found. So the other possibility is that we indeed have this excitonic condensate. We did a calculation using now a much cheaper static mean field LE plus U theory. We found again this excitonic condensate, which gives rise to this kind of complicated arrangement of spin. So the total spin moment per cobalt side is essentially 0, but there is a spin polarization which breaks the spin, the time reversal invariance, and there is an exchange field that acts locally inside the material, and that is felt by the praseodymium moments. So there were also studies by other groups who used RPA, and they also observed this excitonic condensation, and they were able to identify the order parameter and calculate the dispersions of in the ordered phase. Okay, so now I'm getting close to the end of my talk. So how can we actually prove? So this what I showed you, this let's say specific heat, this is rather indirect evidence that there may be excitonic condensation. So how can we prove that we have an excitonic condensate? Well, what one would have to prove is that there is this local coherence between low spin and the intermediate spin, or local coherence between different multiplets, which is of course rather difficult. Another way to prove it, or to bring a strong evidence, would be to observe this excitonic dispersion. But again, as I explained with Rix, it's rather difficult. First of all, because of the Rix resolution. Second, because you don't have access to the full Brillouin zone, at least not for the 3D materials. There was recently a very beautiful study of magnons in ruthenium compounds. So for 4D, you can really map out these dispersions because you are working with much harder X-rays. So what we think the most promising idea is to use this spin structure factor, because as I showed you before and as I show you here again, there is a qualitative change of the spin response when we go from the normal state to the ordered state. In the normal state, you see essentially local moment-like response of the thermally excited high spins. If we go to the ordered phase, we see we have a rather sharp dispersion. Now, if you compare this dispersion with the excitonic dispersions, you can see a similarity between this one and this one. And this similarity is no coincidence. It has actually a rather simple explanation. So if we go back to the relationship between the spin moment and the excitonic operators here, and we realize that when we go to the condensed phase, we can replace one of these operators by a constant. So in our case, the operator or the direction of the order parameter is such that this dy is proportional to I times real number. If we replace this, we see that the sz is proportional to dxr, and this is precisely this correlation function that is similar to the spin structure factor. So we propose that a spin structure factor, which can be easily measured with inelastic neutron scattering, actually can bring us a proof of at least this polar excitonic condensation taking place. There is some first study on calcium cobaltate which shows with rather poor resolution an effect which can be called opening of this gap throughout the Brillouin zone except close to the gamma point, so there is some first encouraging experimental result. Okay, so this takes me to the end of my talk. Before I show my conclusions, let me acknowledge the people that contributed to the results I showed you. Atsushi Harike, a postdoc with me, Juan Afonso, who is a PhD student, Andrei Sotnikov, who was a postdoc in my group, Dominique Geoffroy, who is the guy who is a postdoc and who is responsible for the nice dynamical susceptibilities, and Pavel Augustinsky, who used to be a postdoc with me in Prague and who contributed to the early studies, and then experimentalists from the group of Frank de Groot, who made the RIX experiments on lanthanum cobaltate. So let me just show my conclusions. So excitonic magnetism provide a rather rich physics playground with potentially interesting applications. What somehow hinders the progress in the field, of course, is that we don't have a proven material realization in a simple material. We have just these artificial structures, and we have to work on experimental techniques, on identifying experimental techniques for unambiguous identification of this phase. So let me stop here and thank you for your attention.